Welcome back. In this video, we're going to look at examples of solving integrals using integration by parts. Let's get to it. All right, so here's our first example. We want to integrate x times e to the power of 4x dx. And so the reason we want to integrate this integral using integration by parts is because there's no other integration technique that will allow us to solve this integral, right? We have a product of x and an exponential function which cannot be solved any other way. We can't use u substitution, and we can't manipulate this to make it easier to solve. We need to use integration by parts. And so this is the integration by parts formula right here. We have that the integral of u times dv is equal to u times v minus the integral of v times du. All right, so now this side of the formula, the integral of u times dv, corresponds to the integral we are trying to solve. Within this integral somewhere is going to be our function for u, and then we're also going to have a function for dv. And so what we want to do is rewrite that integral right here to be these two terms right here. And so notice that within this expression, we have v and du, which are not in our original integral. And so where they come from is du will be the result of the derivative of u, and v will be the result of the integral of dv. And so when you're choosing u and dv from your integral that you want to solve, you have to keep in mind that you're going to take the derivative of u and you're going to integrate dv. And you're going to want to set u equal to whatever gets simpler when you take its derivative. And so in this case, if you look at the product of our two functions, we have x and e to the power 4x. Which of these two functions becomes simpler when you take its derivative? Well, if you take the derivative of x, it becomes 1, right? The derivative of x is just 1. And if you take the derivative of e to the power of 4x, well, e to the power of 4x will require the chain rule. It's going to be e to the power of 4x times the derivative of 4x, which is 4. And so that doesn't really get simpler when you take its derivative. Taking the derivative of x gives you a much more simplified answer of just 1. And so it's going to be a better choice to set u equal to x. And so we'll set u equal to x and dv equal to e to the power 4x dx. And so we'll have u is equal to x and dv is equal to e to the power 4x dx. All right, and so now there is an alternate way to determining which function you want to set equal to u. It's a little bit of a trick, and so I'll show it to you here. We use an acronym LIATE, or LIATE if you want to try to pronounce it, and this acronym helps us decide what we should choose to set equal to u. All right, and so the L stands for logarithms, the I stands for inverse trig functions, the A stands for algebraic functions, or polynomials, the T stands for trig functions, and the E stands for exponential functions. And essentially all this is a priority list of what you should set equal to u. So if you have a product of two functions and you know you want to use integration by parts, and you can identify what type of functions you have within this list, whichever one of those functions is higher up in the list, you want to set that equal to u. Okay, and so this is a guideline that you can follow if you'd like. However, it's not going to work for every single integral you see that you want to use integration by parts for. And so that's why I kind of show you the other way of trying to determine which of your functions gets simpler when you take its derivative. Okay, but using a combination of both, maybe using this as a fallback if you're not sure which function gets simpler when you take its derivative. But either way, it comes down to preference. Just try to find a method that works best for you when solving integrals with integration by parts. But back to our example here, let's take the derivative of u and then let's integrate dv. So if we take the derivative of u, we'll have du dx is equal to the derivative of x, which is just 1. Right, the integral of x to the first power is just equal to its coefficient, which is 1, so that's our derivative. And then if we multiply both sides by dx, we will have that du is equal to dx. Okay, and so now let's integrate dv. We will have that the integral of dv is equal to the integral of e to the power of 4x times dx. And now the integral of dv is just equal to v, so we're going to have v is equal to the integral of e to the power of 4x. Now typically, since this is a composite function, we have e to the power of some function other than just x, we would want to use u substitution here, but instead of going through with the u sub process, we can use a little trick for integrating exponential functions, and that trick is that the integral will just be equal to that exponential function, e to the power of 4x, divided by the coefficient of x, right? So in this case, we have e to the power of 4x, and the coefficient of x is 4, and so we will divide by 4. That's just a little trick for when you're integrating an exponential function where you have e to the power of some constant times x. The moment you have x squared or some other function that isn't x to the power of 1, this trick isn't going to work, so just keep that in mind. But if you just have a simple exponential function like e to the power of 4x, this is a nice way to take that integral fairly quickly. Okay, and so now let's use what we have here to rewrite this integral using the integration by parts formula. We will have that this is equal to u times v, and u is x, and v is e to the power of 4x divided by 4. So we will have x times e to the power of 4x divided by 4, and then we will subtract the integral of v, which is still e to the power of 4x divided by 4, and then we will multiply that by du, and du is just equal to dx, and so we'll multiply by dx. Okay, so we used our values of u, dv, du, and v to rewrite this integral into this form using this formula. All right, and so what that did is it gave us an expression with an integral that is easier to solve than the integral that we started with. And so let me show you what I mean. If we simplify, this will be equal to x times e to the power of 4x divided by 4 minus, we can pull out this 1/4 to the outside of the integral, and so we'll have 1/4 times the integral of e to the power of 4x times dx. And now this integral right here is the same integral that we did over here when we were solving for v. And so remember, the integral of e to the power of 4x is just e to the power of 4x divided by 4. And so this is equal to x times e to the power of 4x divided by 4 minus 1/4 times e to the power of 4x divided by 4. And then don't forget to add plus c, since we do have an indefinite integral here. And then multiplying 1/4 by e to the power of 4x divided by 4 will give us a denominator of 16. And so our final answer is that this is equal to x times e to the power of 4x divided by 4 minus e to the power of 4x divided by 16 plus c. And that is the solution to this integral by using integration by parts. Let's look at another example. So here's our next example. We have the integral of the natural log of x divided by x to the 4th power times dx. All right, and so the first thing that we want to do here is figure out what we're going to set equal to u and what we're going to set equal to dv. Now before we do that, we do need to use integration by parts to solve this integral because there's no other way that we could solve it, right? U substitution is not going to work here because we can't set u equal to either of these functions and find its derivative within the integral. So u substitution is going to fail. The only way to solve this integral is going to be through integration by parts. All right, and so I just want to rewrite this integral real quick to make it more obvious what two functions are being multiplied together. This is equal to the integral of the natural log of x times x to the negative 4th power dx, right? We can move this x to the 4th power to the numerator by making that exponent negative. All right, so this is the same integral that we have up here. And now from these two functions, the natural log of x and x to the negative 4th power, we need to choose a u and a dv. Now whatever we set equal to u, it needs to get simpler when we take its derivative. And so let's take a look at each of these functions. The natural log of x, the derivative will be 1 divided by x, and the derivative of x to the negative 4th power will be negative 4 times x to the negative 5th power, right? We multiply the exponent down and then subtract 1 from that exponent, and so this would be its derivative. And so it's hard to say whether either of these derivatives are simpler than their original function. And so the choice for u isn't entirely clear at first, but remember, whatever we choose to set equal to u, the other function is going to be dv, and we will have to integrate that function. And so looking at these two functions, we know how to integrate an algebraic function like x to the negative 4th power, but we don't really know how to integrate the natural log, right? We don't have an easy rule to integrate that function. And so because of that, it's going to be preferable that we set the natural log of x equal to u, so that dv will be a function that we can integrate. And so let's do that. we'll have that u is equal to the natural log of x, and dv is equal to x to the negative fourth power times dx. Okay, so the natural log of x is u, and then x to the negative fourth power dx is dv. Now real quick, if you're a fan of the acronym, I'll bring that up on the screen here. If you were to look at that list, you know that we have a product of a log function times an algebraic function, and so you can clearly see from the list that the logarithmic function is higher up on the list, and so you would know to set u equal to the natural log of x, but I always like to try to look at it a little bit more logically before falling back to that acronym. Okay, and so let's take the derivative of u. We will have that du dx is equal to the derivative of the natural log of x, which is 1 divided by x, and then if we solve for du by multiplying both sides by dx, we will have that du is equal to 1 divided by x times dx. Now, we want to take the integral of dv, so we will have the integral of dv is equal to the integral of x to the negative fourth power times dx. Now, the integral of dv will be v, and that is equal to the integral of x to the negative fourth power. Now we're going to use the power rule of integration here, so we'll add 1 to the exponent and then divide by that new exponent. So we'll have x to the negative third power divided by negative 3. Okay, and so now let's use this information to rewrite this integral using the integration by parts formula. We will have that this is equal to u times v, which will be the natural log, times x to the negative third power divided by negative 3. So we'll have the natural log of x times x to the negative third power divided by negative 3. And then we will subtract the integral of v, which is x to the negative third power divided by negative 3 times du, which is 1 divided by x times dx. So we will have times 1 divided by x dx. Okay? And so if we simplify, I'm going to move this negative out front and then make this exponent positive by moving this to the denominator. And so this will be equal to negative natural log of x divided by 3 times x cubed, right? So this x to the negative third power became x cubed, and this 3 is still in the denominator. I just moved the negative to the numerator. It doesn't matter where you place that negative. It's going to be the same expression either way. Okay, and then for this integral, we can pull this negative 1/3 to the outside, and that will become positive. So we'll have plus 1/3 times the integral of x to the negative third power times 1 divided by x, and I'm going to rewrite that as x to the negative first power, because if we move x to the numerator, that exponent will become negative, and so then we'll multiply by dx. Now the reason I did that is because then we can combine these two functions by multiplying them, because x to the negative third power times x to the negative first power will become x to the negative fourth power by adding the exponents. And so if I clean up my work here, this will be equal to the negative natural log of x divided by 3x cubed plus 1/3 times the integral of x to the negative fourth power times dx. And now we have an integral that we've already solved before when we were working with dv. We have the integral of x to the negative fourth power again, and so this is a pretty simple integral for us to solve. And so let's finish up this solution. This will be equal to negative natural log of x divided by 3x cubed plus 1/3 times x to the negative third power divided by negative 3, which is the integral of x to the negative fourth power, and then don't forget to add plus c. All right, and so then if we move x to the negative third power to the denominator, we'll have x cubed, and then we can multiply 3 and negative 3, and we'll have our final answer that this is equal to the negative natural log of x divided by 3 times x cubed minus 1 divided by 9x cubed plus c, right? 3 times 3 is 9. I brought that negative out front, and then since we moved this to the denominator, we just have 1 in the numerator. And so this is the solution to this integral using integration by parts. All right, so here's our next example. We have the integral of x times arctangent x dx. And the arctangent function is just the inverse tangent function, in case you're not familiar with that notation. All right, and so we're going to need to use integration by parts to solve this integral. And so we need to determine a u and a dv from our integral. And so let's start with u. We know we want to set u equal to the function whose derivative is simpler than the original function. And so in this case, the derivative of x we know is equal to 1. and the derivative of arctangent, or the inverse tangent function, is 1 divided by x squared plus 1. All right, and so we might be tempted in this case to say that x becomes simpler when we take its derivative. However, if we set arctangent x equal to dv, then we would need to integrate the arctangent function, and we don't know how to integrate the arctangent function. At least we don't have a very nice rule for it. We know how to integrate functions into the arctangent function, but we don't know how to integrate that function itself with a specific rule. And so I'm going to argue against setting x equal to u. For that reason, we should set the arctangent function equal to u instead. Now, of course, if you're using the acronym LIATE, then it's a little bit more obvious that we should set u equal to the arctangent function, because inverse trig functions are higher in the list than algebraic functions, okay? So that list is always a fallback if you're really not sure what to set equal to u. Okay, and so let's do that. Arctangent x will be u, and x dx will be dv, and so I'll write that. U is equal to arctangent of x, and dv is equal to x dx. Okay, so if we take the derivative of u, du dx is equal to the derivative of arctangent, which, like I said earlier, is 1 divided by x squared plus 1. And then if we multiply both sides by dx, we'll have that du is equal to 1 divided by x squared plus 1 times dx. And now we'll integrate dv. The integral of dv will be equal to the integral of x dx. And so then we'll have that v is equal to the integral of x, which, if we use the power rule of integration, we'll add 1 to the exponent and then divide by that new exponent, and so we'll have x squared divided by 2. Okay, and so let's use what we have here to rewrite this integral using the integration by parts formula. We will have that this integral is equal to u times v, so we'll have arctangent times x squared divided by 2. So I'll write that. We have arctangent of x times x squared divided by 2, and then we will subtract the integral of v, which is x squared divided by 2, times du. And du is 1 divided by x squared plus 1 times dx. So we have times 1 divided by x squared plus 1 times dx. All right, and so if we simplify, I'm going to pull this 1/2 out to the front, and then I'm going to multiply x squared by arctangent x. I'm just going to change the order that they're being multiplied by. It just looks a little bit nicer if we write it like this. We'll have 1/2 times x squared times arctangent x, and then we will subtract this integral, and I'll pull this 1/2 to the outside, so we'll have 1/2 times the integral of x squared divided by x squared plus 1 times dx. Okay, so I just multiplied x squared by this function, and so now we have this integrand for this integral. Now, how are we going to solve this integral? This is going to be easier to solve than what we started with, right? That's the whole idea of integration by parts. It's going to give us an integral that we do know how to solve, but this one's a little bit tricky. It's not initially obvious how we're going to integrate it, but notice that we have an x squared in the numerator and the denominator, and so we can use that to our advantage and try to get what we have in the denominator in the numerator so that we can have some canceling happen. And so let me show you what I mean. Let's rewrite what we have. This is equal to 1/2 times x squared times arctangent x minus 1/2 times the integral of this function. And now watch what I'm going to do here. I'm going to write x squared plus 1 minus 1 divided by x squared plus 1 times dx. Now it looks like I did something illegal here, but I didn't. We added 1 and subtracted 1 in the numerator, which is just equal to 0, right? 1 minus 1 is 0. So this is still the same numerator we have up here, but now we have x squared plus 1 in the numerator as well as in the denominator. And so we can split this up into two fractions, right? We can have x squared plus 1 divided by x squared plus 1 minus 1 divided by x squared plus 1. So I'm going to rewrite this integral just slightly. We'll keep that same denominator, x squared plus 1, but then we're going to subtract 1 divided by x squared plus 1, and that's still multiplied by dx. Now x squared plus 1 divided by itself is just equal to 1. That's why I did that manipulation, because now this is just going to reduce to become 1. And so I'll rewrite that. This is just going to be 1 minus 1 divided by x squared plus 1. And so if I clean up my work here, we can simplify this further by splitting it up into two separate integrals. And so if we do that, this will be equal to 1/2 times x squared times arctangent of x minus 1/2 times the integral of 1 times dx minus the integral of 1 divided by x squared plus 1 times dx, right? So I'm multiplying 1/2 by this whole integral, which I have split up into two integrals. The integral of the first term minus the integral of the second term. And the reason I did that is it's going to make integrating a little bit easier because we know the integral of 1 is just x, and the integral of 1 divided by x squared plus 1 is the inverse tangent function, right? The integral of 1 divided by x squared plus 1 is arctangent, just like the derivative of arctangent is 1 divided by x squared plus 1. And so what we'll have here is that this is equal to 1/2 times x squared times arctangent of x minus 1/2 times the integral of 1, which I said is x, minus the integral of 1 divided by x squared plus 1, which is arctangent of x. And so we'll close that, and then don't forget to add plus c. And so if I clean up my work one more time here, we can distribute this negative 1/2 to each of these terms, and then we will have our final solution. So this will be equal to 1/2 times x squared times arctangent of x minus 1/2 times x plus 1/2 times arctangent of x plus c. All right, and so this is the final solution to this integral using integration by parts. The resulting integral from using the formula was a little bit tricky to solve, but it's nothing that we couldn't handle. Let's look at another example. So here's our next example. We have the integral from 0 to 1 of x squared times e to the power of x dx. So this time we have a definite integral that we need to solve using integration by parts. And so this adds another level of difficulty, although it's not that much more difficult. We just have to remember that we have bounds of integration this time. And so let's start by figuring out what we're going to set equal to u and what we're going to set equal to dv. Now in this case, we have x squared and e to the power of x. And so which of these two functions, if we set it equal to u, gets simpler when we take its derivative? Well, if we take the derivative of x squared, that will be 2x via the power rule of integration. We multiply that exponent down and then subtract 1 from the exponent. And then the derivative of e to the power of x is e to the power of x. And so in this case, e to the power of x did not get any simpler, but x squared became x to the first power, so we just have 2x, and so that is simpler than x squared. And so I'm going to choose x squared to be equal to u. Now, if you use the acronym from before, you can see that algebraic functions are higher on the list than exponential, and so if you were using that acronym, you could easily see that you're going to set x squared equal to u. All right, so x squared will be u, which means that e to the power of x dx will be dv. And so I'll have u is equal to x squared, and dv is equal to e to the power of x times dx. And so if we take the derivative of u, we'll have du dx is equal to 2x, and then multiplying both sides by dx will give us that du is equal to 2x times dx. Now let's integrate dv. The integral of dv will be equal to the integral of e to the power of x dx, and the integral of e to the power of x is just itself, so we'll have v is equal to e to the power of x. All right, and so let's use what we have here to rewrite this integral. So this will be equal to u times v, which is going to be x squared times e to the power of x. So we'll have x squared times e to the power of x, and then we will subtract the integral of v times du, and v is still e to the power of x, so we'll have e to the power of x, and then multiplied by du, which is 2x dx. So we will multiply by 2x dx. Now remember, this is a definite integral, and so we need to evaluate all of this from 0 to 1, right? Not just this integral, we also need to evaluate this term as well. Okay, so however you want to denote that is fine. This is the way that I choose to do it. It keeps everything straight for me. And so let's simplify a little bit and see what we can do with our new integral. So this will be equal to x squared times e to the power of x minus, let's pull this 2 out to the front of the integral. So we'll have negative 2 times the integral of e to the power of x times x. And I'm going to reorder that multiplication. I'm just going to have x times e to the power of x times dx. And that will be evaluated from 0 to 1. Now you'll notice that in this integral, we have another integrand where we have a product of two functions that the only way to integrate them is by using integration by parts. And so this is very similar to our original integral. However, instead of having x squared times e to the power of x, we have just x to the first power times e to the power of x. So our integral did get simpler, and so if we use integration by parts one more time, it should get even simpler, and we should be able to get our final solution. So remember, sometimes you do need to use integration by parts more than once in order to solve a given integral. Okay? And so we're going to have to pick a new u and a new dv, and just so I don't get them confused with our previous choices, I'm going to add subscripts. Now you don't have to do this for your work, but I'm going to do it so that you don't get confused with my work. So I'm going to add subscripts here for u, and I'm going to add a subscript for v as well. So we have u sub 1 and v sub 1. Now we're going to have u sub 2 and v sub 2. So let's do that. Let's pick a new u and a new dv. Just like last time, I'm going to set u equal to our algebraic function and set dv equal to e to the power of x dx. And so we'll have u sub 2 is equal to x, and dv sub 2 is equal to e to the power of x dx. All right, so x is u, and e to the power of x dx is dv. And so if we take the derivative of u sub 2, we'll have du sub 2 divided by dx is equal to 1, right? That's the derivative of x, which means that du sub 2 is equal to dx if we multiply both sides of that equation by dx. And then let's integrate dv sub 2. The integral of dv sub 2 will be equal to the integral of e to the power of x dx. And the integral of e to the power of x, once again, is just e to the power of x. And so we have that v sub 2 is equal to e to the power of x. All right, and so let's use our new information to rewrite this integral. And I'm going to have to write a little bit smaller here. So this is equal to x squared times e to the power of x minus 2 times our new terms that will represent this integral, right? We have negative 2 times this integral, and if we're going to rewrite this integral with these two terms from our formula, we need to multiply negative 2 by both of those terms, and so we need these parentheses. Okay, so we're going to have u times v, so we'll have x times e to the power of x, so I'll write x times e to the power of x, and then we will subtract the integral of v, which is e to the power of x, times du, which is dx. And so I'll write dx. Okay? And so then remember that this is all evaluated from 0 to 1. Okay? And so if I clean up my work here, we can simplify. This will be equal to x squared times e to the power of x, and then let's distribute negative 2 to each of these terms. So we'll have negative 2x times e to the power of x plus 2 times the integral of e to the power of x dx evaluated from 0 to 1. Right, so negative 2 times this negative integral will give us positive 2 times that integral. All right, and so the integral we are left with now is a pretty simple integral that we can evaluate. We know that the integral of e to the power of x is just e to the power of x, and so I'll just rewrite that. We'll have 2 times e to the power of x, and that will be evaluated from 0 to 1, and I'm just going to erase that. Okay, so now let's evaluate this expression at 1, and subtract the evaluation at 0, and then we will have the answer to our definite integral. So this will be equal to 1 squared times e to the power of 1 minus 2 times 1 times e to the power of 1 plus 2 times e to the power of 1 minus 0 squared times e to the power of 0 minus 2 times 0 times e to the power of 0 plus 2 times e to the power of 0. Okay, so I just plugged 1 in for all of these x's, and then subtracted, plugging 0 in for all of these x's. And so if I clean up my work here, we can simplify. This will be equal to 1 times e minus 2 times e plus 2 times e minus 0 squared is 0. So this whole term is 0. And we also have a 0 being multiplied for this term, so that's also 0. And so we're just going to have plus 2 times e to the power of 0, and e to the power of 0 is 1. So we have minus 2 times 1. Okay, and so if we simplify, notice that we have a positive 2e and a negative 2e. Those are going to cancel out to become 0. And so what we have here is that this is equal to e minus 2, right? 1 times e is e, and 2 times 1 is 2. And so e minus 2 is the solution to this definite integral. let's look at one more example for this video. All right, so here's our last example. We have the integral of e to the power of 2x times cosine of 3x dx. Okay, so we're going to need to use integration by parts to solve this integral because none of our other integration methods are going to work. We have a product of an exponential function and a trigonometric function. And so what we want to do is determine our u and our dv for our formula. Now we typically want to set u equal to the function that gets simpler when we take its derivative. However, watch what happens in this scenario. If we take the derivative of e to the power of 2x, that's going to be equal to e to the power of 2x times the derivative of its exponent 2x, which is just 2. And so that is the derivative of e to the power of 2x. And then if we look at the derivative of cosine of 3x, that's going to be equal to negative sine of 3x times the derivative of that inside function, which is just 3. And so in either case, the derivative of both of these functions is not getting any simpler, right? And so what do we do in this scenario? Well, if we reference our acronym, LIATE, you can see that trig functions are higher up on the list than exponential functions. And so it looks like we want to set u equal to our trig function. Now, I just want a quick note. I pointed this out in my lesson video. You could actually set u equal to either of these functions in this case, and you would still be able to solve this integral using integration by parts. We just put trig functions before exponential functions so that we have a nice acronym that we can actually pronounce. But either way, you can set either of these functions equal to u, and you would still get the correct answer. But I'm going to choose to set u equal to our trig function, and so that means u will be cosine of 3x, and dv will be e to the power of 2x dx. Okay, so u is equal to cosine of 3x, and dv is equal to e to the power of 2x dx. All right, and so let's take the derivative of u. We'll have that du dx is equal to the derivative of cosine, which is negative sine, and then we'll keep that same inside function, and then multiply by the derivative of that inside function. Right, we're just using the chain rule for derivatives here, and the derivative of 3x is 3, because when you take the derivative of x to the first power, it's just equal to its coefficient, so we'll multiply by 3. And then if we solve for du by multiplying both sides by dx, we'll have that du is equal to negative 3 times sine of 3x times dx. Okay? And then we'll integrate dv, so the integral of dv will be equal to the integral of e to the power of 2x dx, and so that will give us that v is equal to that integral. And so a quick trick, I think I showed this for an earlier example, but a trick to integrate an exponential function quickly, where you just have e to the power of some constant times x, it's just going to be that exponential function, e to the power of 2x, divided by that constant, which is 2. And so that will be our integral of this function. And so now let's use what we have here to rewrite this integral in this form. So this will be equal to u times v, so we'll have cosine of 3x times e to the power of 2x divided by 2. So I'll write that, cosine of 3x times e to the power of 2x divided by 2. And then we will subtract the integral of v, which is still e to the power of 2x divided by 2, times du, which is negative 3 times sine of 3x dx. And hopefully I can fit that all in here. We'll have negative 3 times sine of 3x times dx. Okay, and so let's rewrite this. Let's make it a little bit nicer. This will be equal to e to the power of 2x divided by 2 times cosine of 3x. I just reordered the multiplication here. It's not a big deal if you leave it like this. I just prefer to write it this way. And then for this integral, notice that we have a negative 3 in here, and so we can pull that out, and this will become positive. So we'll have positive 3 times this integral, but then we also have this 1/2 that we can pull out, and so we'll have plus 3 divided by 2, or 3/2, times the integral of e to the power of 2x times sine of 3x dx. Okay, so hopefully you're able to follow that. I pulled this negative 3 out to the front, so we had plus 3, and then I also brought out this 1/2, so now we have 3/2 out in the front of the integral. All right, and so if we look at the integral that we have here, it doesn't seem like it got any simpler than what we had before, right? We had the integral of e to the power of 2x times cosine of 3x, but now we have the integral of e to the power of 2x times sine of 3x. So it didn't seem to get any simpler. However, if we use integration by parts again on this integral, something pretty cool is going to happen. So what we're going to want to do here is pick a new u and a new dv for this integral, and I'm going to choose u to be the trig function again and set dv equal to the exponential function just to be consistent. And so if we do that, I'm just going to separate our previous u and v from our new ones. And I'm also going to add a subscript like I did in a previous example so that you don't get confused with my new u and my new dv compared to the old ones from the previous integral. So I'm going to say that this is u sub 1 on this side, and then we'll have v sub 1 over here. Okay? So now for our new integral, I'm going to set u equal to sine of 3x, and I'm going to set dv to e to the power of 2x times dx. So we'll have u sub 2 is equal to sine of 3x, and dv sub 2 is equal to e to the power of 2x times dx. Now this is the same as what we had up here for dv sub 1, so this is going to be pretty easy to determine. I'm going to do that first. The integral of dv sub 2 will be equal to the integral of e to the power of 2x dx, which means that v sub 2 is equal to e to the power of 2x divided by 2. That integral will remain the same. Now for u, we have a different function from what we had before, so we need to take that derivative. We'll have that du sub 2 divided by dx is equal to the derivative of sine, which is cosine of 3x, and then we want to multiply by the derivative of that inside function. And just like before, the derivative of 3x is 3. And so du sub 2 is equal to 3 times cosine of 3x times dx. All right, and so if we rewrite this integral, I'm going to have to write a lot smaller here. This is going to be equal to e to the power of 2x divided by 2 times cosine of 3x plus 3 halves times our new terms that will represent our integral. Okay, so 3 halves is multiplied by this whole integral, which we are going to now rewrite with 2 new terms using these values. So we'll have u times v, which is sine of 3x times e to the power of 2x divided by 2. So we'll have sine of 3x times e to the power of 2x divided by 2, and then we will subtract the integral, and I'm going to have to rewrite that parenthesis. I'm going to put it over here. And inside the integral we'll have v, which is e to the power of 2x divided by 2 times du, which is 3 times cosine of 3x times dx. And I just barely fit that in there. And so if I clean up my work here, we can rewrite this so that it's easier to see. Okay, so this will be equal to e to the power of 2x divided by 2 times cosine of 3x plus 3 halves times sine of 3x times e to the power of 2x divided by 2 minus the integral of e to the power of 2x divided by 2 times 3 times cosine of 3x times dx. Okay, so I just rewrote exactly what we had up here so that it's more readable as we continue on with solving this integral. And so if I clean up my work again, we can simplify by distributing this 3 halves through this quantity. So this will be equal to e to the power of 2x divided by 2 times cosine of 3x plus 3 halves times sine of 3x times e to the power of 2x divided by 2 minus 3 halves times the integral of e to the power of 2x divided by 2 times 3 times cosine of 3x times dx. Okay, and so now notice that we can multiply 3 halves by this 1 half here, and so we'll have 3 times e to the power of 2x divided by 4 if we multiply the 2's together. And so if we rewrite that, this is equal to e to the power of 2x divided by 2 times cosine of 3x plus 3e to the power of 2x divided by 4 times sine of 3x. And then we will subtract this integral, which we can pull another 3 halves to the outside. We have this 3 and this 2 in the denominator. So 3 halves times 3 halves is 9 fourths. And that will be multiplied by the integral of e to the power of 2x times cosine of 3x dx. Okay? And so if I clean up my work again, it almost seems as though we hit a dead end because we have another integral that it looks like we need to use integration by parts for in order to solve. But notice that this integral looks just like what we started with, right? we had the integral of e to the power of 2x times cosine of 3x dx, and we have that right here. And so if these terms right here are equal to this integral, we can rewrite what we have here to represent that, and that will lead to something pretty cool. So we'll have that the integral of e to the power of 2x times cosine of 3x dx is equal to all of these terms, right? This is just our integral up here. And so we'll have e to the power of 2x divided by 2 times cosine of 3x plus 3 times e to the power of 2x divided by 4 times sine of 3x minus 9/4 times the integral of e to the power of 2x times cosine of 3x dx. And so now what we can do is combine like terms, or more specifically, like integrals, right? Both of these integrals are the same, except this integral has a coefficient of negative 9/4, and this integral has a coefficient of 1. So if we add this integral to both sides of the equation, it will eliminate this integral from this side of the equation, and then we will add 9/4 to 1 to combine our integrals. And so if we have 1 plus 9/4, 1 is the same as 4/4, and so 4/4 plus 9/4 is 13/4, and so we will have 13/4 times the integral of e to the power of 2x times cosine of 3x dx. And this is the result of adding this integral to both sides of the equation. Now we have 13/4 times this integral, and that will be equal to these other two terms. And so we'll have e to the power of 2x divided by 2 times cosine of 3x plus 3 times e to the power of 2x divided by 4 times sine of 3x. And now all we have to do to finish solving this integral is divide both sides by 13/4, and then we will have that this integral is equal to these two terms divided by 13/4. And so if I clean up my work here, we will have that the integral of e to the power of 2x times cosine of 3x dx will be equal to each of these terms divided by 13/4. And remember that dividing by a fraction is the same as multiplying by the reciprocal of that fraction. And so if we flip the numerator and the denominator, we will multiply each of these terms by 4/13. So we'll have 4/13 times e to the power of 2x divided by 2 times cosine of 3x plus 4/13 times 3 times e to the power of 2x divided by 4 times sine of 3x. And so if we simplify, these two 4's will cancel out, and then 4 divided by 2 will be equal to 2. And so our final answer is that this integral, which is the same as this integral up here that we're trying to solve, is equal to 2 times e to the power of 2x divided by 13 times cosine of 3x plus 3 times e to the power of 2x divided by 13 times sine of 3x, and then don't forget to add c to the end of that answer. And so this is the solution to our integral using integration by parts. Okay, and so with that, this was the last example for this video. And so if you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.